Good day, we'll now discuss graph coloring. So in graph coloring, each vertex of a graph will be assigned one color in such a way that no two adjacent vertices have the same color. Say for example, if we have this illustration. Okay, so we have this. Say for example, if I will color this red, okay, since they are adjacent, this one and this one are adjacent, I cannot color this red because again, no two adjacent vertices have the same color. So I may color this, say for example, blue. Okay, so since this is blue, these two, this one and this one, cannot be blue. So I can color these two with another vertex, another color. Now, if you notice, I have red here, so I can color this one again with red because these two are not adjacent. Okay. Again, these two are not adjacent, so I may color this one as red. Okay. Next, I cannot color this red, although these two are not adjacent, but these two or these two are adjacent, so I cannot color this one as red. But if you notice, blue, this color blue here, this vertex here is not adjacent to this vertex. So I can color this one as blue. So therefore, I have this graph coloring. Okay, so I colored this graph using two colors, the red and the blue. Again, in graph coloring, each vertex of a graph will be assigned one color in such a way that no two adjacent vertices have the same color. Now, uh, this is very easy if you come to think of it, because if this is just the concept, then of course I can color everything with different color, right? So I can just color this red, blue, orange, indigo, and so on. Now, the interesting idea in graph coloring is this. We must determine the minimum number of distinct colors to be used so that each vertex of a graph is colored such that no two adjacent vertices have the same color. So in this case, we must see to it that the number of colors that we use in coloring a graph is the lowest or the minimum. Okay, so without this interesting idea or additional requirement, then of course it's very easy to color the vertices with different colors. Now, before we proceed, let's have this definition, a planar graph. A planar graph is a graph that can be drawn so that no edges intersect each other except at vertices. Take note, when we say drawn, it can also be, we can also use the word redrawn. Now, if you can redraw, now, if you can redraw a given graph without intersection of their edges. Okay, for example, this one, this is planar since there are no intersections, or there is no intersection at all. And for this one, it's non-planar because of course there are intersections, and we cannot redraw this one without intersecting the edges. Say for example, this edge, I will redraw this one here. Okay, so I will redraw this one here. But if I will redraw this one here, so again, they will intersect. Okay, so they will intersect. So how about this one? So if I do this, then of course, I will also stretch this one here, redraw again. There are intersections. Okay, for this particular graph, you cannot redraw this one. Okay, redraw this one without intersecting its edges. Okay, when we say intersect, the edges goes like that. This one, intersection, 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 intersection. Now, is this planar? Of course, by just looking at this is not planar because there is an intersection here, right? But this is actually planar. Why? Because we can redraw this one. One way of redrawing this is this one. So this particular edge can be redrawn in this manner, which is this one. And now there are no intersection. So this is planar. Or if this will be our top view, say for example, this is our top view, this one. Okay, looking at a graph like this is our top view, and this triangle here is our base. Then of course we can view this graph like this. So with this, there are no intersecting edges. Okay, so this graph actually is planar. Again, a planar graph is a graph that can be drawn or redrawn so that no edges intersect each other except at vertices. Now, is this planar? You may pause the video and try to redraw this graph without intersecting its edges. But the answer is no, because we can't redraw this in such a way that it is planar. Now, the minimum number of colors needed to color a graph so that no edge connects vertices of the same color is called the chromatic number. Okay, it's the chromatic number. Now, we have this theorem. The chromatic number of a planar graph is at most 4. So the minimum number of color to color a planar graph is at most 4. So meaning it can be 1, 2, 3, or 4. The maximum number of color is 4. Now consider the complete graphs K4 and K5 and determine their chromatic number. Now, this one was shown already that it's planar. And of course, K5 is not planar. So these two were shown that they are not, that K4 is planar and the other one is non-planar. So since K4 is planar, then according to this one, the number of chromatic or the chromatic number is at most 4. Okay, so the chromatic number is at most 4. So you may choose colors for this one. So for the first one, for K4, let's try if we have these colors. Say for example, this is yellow. If this is yellow, then of course, do not color these other 3 as yellow because they are connected to this vertex. So you may choose another color. Say for example, for this one, I may choose blue. So since this is blue and the other 2 vertices are connected to this, then I cannot color these 2 as blue. So I will choose another color, say for example, green. And this one is connected to green. Then of course I cannot use the same color, so I will choose another color, so red. Thus, what is our chromatic number? How many colors? We have yellow, 1, blue, 2, green, 3, and red, 4. So the chromatic number of K4 is 4. Now how about K5? Let's try. Say for example, this is yellow. Since 2 is connected to this one, and the others are also connected to yellow, then of course we cannot color these with yellow. So let's have this blue. So the other 3 are connected to blue, so I cannot use blue. So I will choose another color, say red. These 2 are also connected to red, so I cannot color them red. So say for example, we have green. And this one is connected to green, so I cannot color this green. So let's have violet. Okay, so in this case, the chromatic number is 1, 2, 3, 4, 5. Okay, so we have this. And this one. So in general, in complete graphs, all the vertices are adjacent. Take note, in complete graphs, all vertices are adjacent. Thus, each vertex must have distinct color because all the vertices are adjacent. Thus, the chromatic number of every complete graph Kn is the number of vertices n. That is why this one is a complete graph, so K4. So the number of, the chromatic number is 4, which is the number of vertices, and this is K5, so the number of vertices is 5, as well as the chromatic number. Because again, all the vertices are adjacent. So let's try this. Color the graph and give its chromatic number. So we have Herschel graph, Groch graph, and Petersen graph. So let's try. Say for example, I will color this blue. Okay, so I will color this one as blue. So this one. So since this is blue, I cannot color this with blue. I cannot color this with blue. Okay, but I can color this one with blue. And this one again with blue because they are not adjacent. This one again, so it's not adjacent to blue, so let's have this as blue. This is adjacent, so not blue. Okay, so this is blue. Next, for this part, so let's try red. So if it's red, then of course these two are not adjacent, so I can color this red. These two also, I can color this red. This one I can color this red, and I can color this red. So what is now the chromatic number? How many colors did we use? Only two, the red and the blue. So meaning the chromatic number is 2. And if you notice, this is a planar graph. So according to the four color theorem, if it's a planar graph, then the graph or the chromatic number is at most 4. So 4 is the maximum. So in this case for Herschel, the chromatic number is 2. Another example, the Groch graph. So say for example, I will color the center green. So these 5 here are adjacent to green, so I cannot color them green. So this one is not adjacent to green, so I can color this green. These two are adjacent to green, so I cannot color these two as green. But this one is not adjacent to green, so I can color these two green. Since this is green, so I cannot color this as green. Okay, next. I will color this as red. Red. Okay, so these other 5 are not connected at all or are not adjacent. So I color this as red, red, and red. Okay. So since this is red, I cannot color this red, right? This is red, so I cannot color this as red. Okay, this is red, so this should not be red. So I will choose another color. Say for example, violet. Okay, so if this is violet, then of course I can color the other one also as violet because they are not adjacent. I cannot color this one as violet because it's adjacent to this. So I can choose another color. Say for example, yellow. So how many colors did I use? I use green, blue, red, I mean red, violet, and then yellow. Okay, so actually the chromatic number of Groch graph is 4. Now last, this is a Petersen graph, so it's not planar. So of course, we cannot say that the maximum chromatic number is 4. So the 4-color theorem is not applicable. But let's try coloring this graph. So I can have yellow here. So if this is yellow, so these 3 cannot be yellow, but this one can be yellow. If this is yellow, so this one cannot be yellow. This can be yellow, and this one can be yellow. Okay, next. So since this is yellow, I can choose another color for this one. Say, for example, red. I can color this red and color this red. I cannot color this red because it's adjacent to red. I cannot color this yellow because it's adjacent to yellow. So I can choose another color for this one. So say, for example, blue. So they are not adjacent, so I can color this blue, and also this one I can color this blue. So I use yellow, red, and blue. Okay. So actually the chromatic number here is 3. Okay. So the difficult part here in graph coloring is for you to find out the minimum number of colors to color the graph. Okay, so take note of the word minimum. Now, when we say chromatic number, it should be the lowest number, the minimum number of color. Okay, so maybe if you make some practice or other make or use other colors of this one, so maybe you can have 5, you can have 4, but of course the final answer, since we're talking about chromatic number, it should be the lowest number of color. Okay, so we have this. Okay. Now, let's have one application for this one. 6 college accreditation committees need to hold meetings on the same day, but some teachers belong to more than one committee. In order to avoid members missing meetings, the meetings need to be scheduled at different time slots. So use graph coloring to determine the minimum number of time slots needed. So we are given with this table. So of course, we have how many committee? 1, 2, 3, 4, 5, 6. So we have FI for faculty instruction, faculty development, outreach program, physical facility, library facility, and student welfare. And this excess here determines that they are connected. Okay, so the teachers are from this department or from this committee and at the same time from the other committee. So faculty instruction and faculty development. So we have this. Then faculty instruction, FI and OP. That's why we have this. And then we have the library facility. So we have this. Faculty development and faculty instruction. So we already connected this one. Then we have physical facilities. So here. Next, library facilities. So we have this one. And the student welfare. Next, outreach program and FI or the faculty instruction. Then we have physical facility, so this one. And we have the two library facility and student welfare. So we have this one and this one. For physical facility, it's connected to FD and OP and SW. So FD, OP, and SW. And so on. So we have this graph. Okay, so we will now apply the graph coloring. So I can color this one as yellow. So if this is yellow, then of course this cannot be yellow, this cannot be yellow. Okay, this can be yellow, this cannot be yellow, and this can be yellow. Okay, so take note these two are connected. Okay, so say for example, I will choose SW as my other yellow. Okay, so there are two choices for the second yellow. It's either SW or PF. So you choose. Next, since these two are yellow, the others cannot be yellow at all because they are adjacent to these other two. Now let's have FD. Say for example, this is green. So if that is green, then of course they are not connected. So obviously this is green and the other two cannot be green because they are connected to FD. And lastly, for this one, I can color this red. If this is red, they are not connected or adjacent, so I can color it again with red. So that's why we have this. So the chromatic number is 3 since we used yellow, green, and red. 3 colors only. Hence, the minimum number of time slots necessary to ensure that all faculty members can attend all the meetings is 3. So specifically, we have these. So faculty instruction and student welfare must have the same schedule. Green on the other schedule, FD and OP, and another schedule for LF and BF. Application number 2. The fictional map below shows the boundaries of barangays on a rectangular town. Represent the map as a graph. Letter B, find a coloring of the graph using the fewest possible number of colors, so that is the chromatic number. And letter C, color the graph according to the graph coloring theorem. So solution, represent each barangay using vertices. So this was the picture. So I can label this as A, H, G, B, J, I, C, D, E, F. So these barangays will become the vertices. So I have these barangays A, H, G, B, J, I, C, D, E, F. Now looking at A, what are the other barangays connected to this or adjacent? We have H, that is why it's connected to H, and B, that is why it's connected to B. Now let's look at H. What are the barangays that have adjacent boundary? So we have A, so we have the A. We also have B, so that's why it's connected to B. And then we have J, that's why it's connected to J. We have I, so it's connected to I. And we have G, that's why it's connected to G. Now let's look at G. G shares a boundary with H, so it's connected to H. G shares a boundary with I, so we have I and F. Next for B, we have A, H, so A, H, J, and C. So that's why we have J and C. Next for J, we have H, so that's why we have H. We have B, we have I, so there is a small here for I and J. Small boundary shared between the two vertices or towns. Then J and D. For I, we have H, G, F, E, D, J. So that's why it's connected to all of these. H, G, F, E, D, J. And for F, it's connected to G, I, E. So G, I, E. And for E, it's D, I, F. So that's why we have this now as our representation of each barangay into its vertices. Next is to color this one. So we can use this as our graph coloring. Okay, so by the way, okay, so it should be connected here and this one also. Okay, and also this one. Okay, but of course, the same coloring will hold or still holds. Okay, the same coloring still holds. So how many colors? We have yellow, we have red, and we have green. So the chromatic number here is 3. So then the last step is of course to color each barangay using the color assigned to it. So A is yellow. H is green, G is yellow, B is red, J is yellow, I is red, F is green, E is yellow, D is green, and C is yellow. Okay, so if you notice, there are no two towns that shares with the same color. Okay, so in graph coloring, so you should be mindful of the concept that no two adjacent vertices must have the same color. And when we talk about chromatic number, it should be the minimum number of colors in coloring a graph. Thank you for listening.